The most common method to synthesize azobenzene is through the coupling of an aromatic amine such as aniline with a diazonium salt. This reaction proceeds via electrophilic aromatic substitution. Next, dehydrogenation, another method, involves removing hydrogen from hydroxyl compounds to form azobenzene. This can be achieved using catalysts such as palladium or platinum. Dimerization reactions are also employed where two nitrobenzene molecules are reduced and then coupled to form azobenzene. NMR provides detailed information on the molecular structure, mass spectrometry confirms the molecular weight, and FTIR identifies the functional groups. Understanding these synthetic methods and their biological impacts is essential for developing new, safer, and less toxic materials and application. Composed of two phenyl rings joined by a nitrogen double bond nitrogen, it can switch between two distinct geometric forms, trans and cis, when exposed to the red wavelengths of light. Due to its reversible photoisomerization, azobenzene is pivotal in material science and biology. According to Volaric et al. 2022, azobenzene derivatives are key components in photoresponsive materials used in liquid crystal displays, optical storage, and light-driven power units. In biology and medicine, azobenzene's photoresponsive properties are being explored for innovative applications such as molecular switches and photoresponsive drug delivery systems, contributing to advancements in disease identification and treatment and personalized medicine by DiMartino et al. 2022. Azobenzene's remarkable properties and versatile applications continue to drive scientific and medical advancement, promising a bright future in various fields. These are the two examples of previous studies: multi-stable conventional azobenzene liquid crystal actuators using only visible light, the decisive role of small amounts of unpolymerized monomers, research by Frederick, Engels, and Albert in 2022, and meta-substituted asymmetric azobenzenes, insights to in structure property relationship by Sana et al. 2024. Azobenzene and its derivatives are renowned for their photochromic properties, essential in smart materials, molecular switches, and optical devices. However, challenges in synthesis and characterization hinder their broader application. Studying the biological activities of azobenzene reveals potential applications in antimicrobial and anti-inflammatory therapies, unlocking new therapeutic potentials. To address these challenges, a comparative analysis of synthetic methodologies is essential to identify efficient and precise methods for high-quality azobenzene production.
The objective of this study are to compare different synthetic methodologies for determining the structure of synthesized azobenzene, to characterize synthesized azobenzene using nuclear magnetic resonance NMR spectroscopy, mass spectroscopy, and Fourier transform infrared spectroscopy, and to study the biological activities and impact of azobenzene. I will briefly discuss my literature review on azobenzene, focusing on its synthesis methods, characterization, biological activities, and environmental impacts. First and foremost, the synthesis methods of azobenzene. In our study, azobenzene is primarily synthesized through coupling mechanism, dehydrogenation, and dimerization. This process is efficient and produces azobenzene with high yields and purity. Next, the structural characterization of azobenzene. Characterizations of azobenzene involve techniques such as NMR, MS, FTIR, and which confirm its structure and purity. Regarding the biological activities of azobenzene, azobenzene exhibits significant antimicrobial, anti-cancer, and antioxidant properties. These activities make it a potential candidate for pharmaceuticals and therapeutic application. Last but not least, the environmental impacts of azobenzene. While azobenzene is beneficial in many fields, its environmental impact cannot be ignored. Azobenzene derivative can be toxic to aquatic life, highlighting the needs for responsible disposal and management. In conclusion, azobenzene synthesis, characterization, biological activities offer valuable insights, but its environmental effect require careful consideration.
For methodology, we use dehydrogenation of hydroxybenzene. So we begin by setting up the reaction in a 10 ml tube with our substrate, hydroxybenzene. So ethanol is chosen for its green solvent and will be added to the mixture. The reaction is carried out in a room temperature for about 2 hours and using third butyl nitrite as a catalyst. This reaction is great because the reaction yield an impressive 69% of S-aroma 1,2-biphenyldiazine from the previous study. So the final product appears as an orange solid, will be confirmed by NMR spectroscopy, showcase the efficiency and the sustainability of this method for biological impacts of azobenzene compounds, focusing on their antimicrobial and anti-cancer properties. For the antimicrobial activities, we will test azobenzene's derivative against bacterial strains like E. coli and S. aureus using the disk diffusion method to measure the inhibition zones. Then we determine the minimum inhibitory concentration to gauge the effectiveness. And for anti-cancer activity, we will conduct the vitro assays on MCF7 and HeLa cell lines. So the case study involved azobenzene highlight the potential application in treating bacterial infection and cancer.
This is our timeline where we start our research at May 2024 and ends at March 2025.
As a result, we will compare different synthetic methods for azobenzene, focus on azocoupling, dehydrogenation, and dimerization to identify the most efficient routes. The synthesized compound will be analyzed by NMR, IR spectroscopy, and mass spectroscopy for detailed structure information. Biological studies will be evaluate the antimicrobial and anti-cancer activities of azobenzenes. So this finding will provide valuable insight into the synthesis, characterization, and potential biological use of azobenzene.